This video is brought to you by mywayteaching.com.
So here is the example 5. A woman pushes a trunk on a railway platform which has a rough surface. She applies a force of 100 Newton over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with the distance to 50 Newton. The total distance through which the trunk has been moved is 20 meter. Plot the force applied by the woman and the frictional force, which is 50 Newton. Calculate the work done by the two forces over 20 meter. Okay, say a woman he pushes a trunk on a railway platform on a rough surface. And first of all, she applies a force of 100 Newton over a distance of 10 meter. But after that, she'll get tired, isn't it? And the force applied force reduces linearly with the distance to 50 Newton, 100 to 50 Newton. Up to 10 meters, it was 100 Newton force, but after that, the force is reduced to 50 Newton with the distance, and the total distance through which the trunk has been moved is 20 meters. So now plot the force applied by the woman and the frictional force, that is the frictional force on the rough surface which is applied on that trunk is 50 Newton, and even calculate the work done by the two forces over 20 meter. Okay, so here is the solution. Up to 10 meter the force was 100 Newton, and from 10 meter to 20 meter the force starts reducing, and at 20 meter it becomes 50 Newton. You can see that in the graph. Okay, see, this is the plot of the force F applied by the woman and the opposing frictional force F versus displacement. Okay, see, the plot of the applied force is as shown in this figure, isn't it? Yes. See, at x is equal to 20 meter means at this point where n is not equal to 0, the frictional force is how much? 50 Newton, isn't it? It opposes the motion and it acts in the direction opposite to F. Since it opposes the motion, it acts in the direction opposite to the force F. So we can say it is therefore shown on the negative side of the force axis. Okay, it is shown on the negative side, not on the positive side, because this is the opposing force for the force. So the work done by the woman is nothing but WF, we can say. The work done by the woman. Okay, that is WF, that is given by area of the rectangle ABCD. You can see here. Okay, and area of the trapezium, that is TEID. This is the work done by the woman. So area of the rectangle, that is ABCD, plus area of the trapezium, CEID. Okay, so we can write this, the rectangle, that is 100 into 10, length into breadth, the area, isn't it? We know that. And for this trapezium, it is given by half into the sides 100 plus 50, and it is multiplied with the 10, the distance. Okay, so that is given by 1000 plus 750. 2 ones are 2 fives are. That is the force, the 1750 joules is the work done by the woman. So now let us see what is the work done by the frictional force. Okay, that is another part of it. That is given by WF, that is equal to area of AGHI, that is again rectangle. That is what the work done by the frictional force. That is minus 50 into how much? 20, isn't it? That is given by minus 1000 joules. So the area on the negative side of the force axis has a negative sign. So this is the simple solution for the two simple problems. Okay. So now let us move to the next part, that is the work energy theorem for a variable force. Okay, the work energy theorem for a variable force. So now we know, no, the idea, we have the idea about work and kinetic energy, isn't it? To prove the work energy theorem for a variable force. So we confine ourselves to one dimension. So let us start with the time rate of change of kinetic energy. Okay, the time rate of change of kinetic energy is given by dk by dt, which is nothing but d by dt, and the kinetic energy is half mv square, isn't it? Yes. So that is equal to m dv by dt into v. And using the Newton's second law, this dv by dt is nothing but a. So m into a gives the force, isn't it? We can write it as f into v. So velocity can be written as dx by dt, isn't it? So thus we can write dk is equal to f into dx. Okay. So integrating from the initial position xi to the final position xf on both the sides, we get initial position xi to the final position xf. Okay, here it is ki to kf. Okay. So if you integrate it with respect to dk, we get kf minus ki in this the LHS and RHS. The integration of xi to xf dx is nothing but the work done. Okay. So thus the work energy theorem is proved for a variable force. See, this work energy theorem is very useful in a variety of problems. Okay. In general, it even incorporate the complete dynamic information of Newton's second law. It is just an integral form of the Newton's second law. So Newton's second law is a relation between acceleration and force at any instant of time, isn't it? Whereas work energy theorem involves an integral over an interval of time. So, in this sense, the temporal information which is contained in the statement of Newton's second law is integrated over and it is not available explicitly. See, another observation is that Newton's second law for two or three dimensions is in vector form, whereas the work energy theorem is in scalar form. So, in the scalar form, information with respect to directions contained in Newton's second law is not present because scalar quantities will not be having any directions, isn't it? Yes. So, now let us see one more simple problem. So the problem is a block of mass m is equal to 1 kg moving on a horizontal surface with speed vi is equal to 2 meter per second enters a rough patch ranging from x is equal to 0.1 meter to x is equal to 2.01 meter. The retarding force Fr on the block in this range is inversely proportional to x over this range, where Fr is given by minus k by x for where x is ranging from 0.1 to 2.01 meter and Fr is equal to 0 for x less than 0.1 meter and greater than 2.01 meter. So where k is given by 0.5 joules. So what is the final kinetic energy and speed Vf of the block as it crosses this patch? Okay, that is the question. So we already know the expression how to find out the value of Kf. Okay, the final kinetic energy is given by K initial plus the range is given by 0.1 to 2.01, isn't it? So that is minus k by x into dx. Okay. So this is half m vi square. So here we can take minus k outside. The integration of 1 by x is ln x. We know that, isn't it? So here the range is given by 0.1 to 2.01. Okay. So here they have given the velocity as well as the mass. Mass is 1 kg and velocity is 2 meter per second. So half into 1 into 4. Okay. So minus of the value of k, it is given as 0.5 joules, isn't it? So and ln 20.1 because it is 2.01 by 0.1. Okay, so that we can write it as 2 minus 0.5 ln 20.1. So that is 2 minus ln 20.1 into 0.5 gives 1.5. It is nothing but 0.5 joules. So Vf is equal to the square root of 2 kf by m. So we know the value of kf and even m. So it is 1 meter per second. So ln is here. Ln is nothing but what? It is the natural logarithmic symbol ln. And we know one property of this ln x to the base e is nothing but we can write this as 2.03 ln is changed to log x to the base 10. Okay.